Right. Good evening, students. In this class, we will be looking at the Dalton's law of partial pressures. And in the previous class, we have completed this part, that is Avogadro's law and ideal gas equation. We have completed till here, and now we are going to start this properties of mixture of gases. In that, first topic is Dalton's law of partial pressures. So we will be looking at this Dalton's law of partial pressures today. Dalton's law of partial pressures. So what does this Dalton's law of partial pressures say? It states that it states that the total pressure of a mixture of gases is equal to the sum of partial pressures of those ideal gases. So if we look at this particular statement, we have two keywords, that is total pressure of the mixture. Total pressure of the mixture is equal to the sum of the partial pressures of those ideal gases. So here you will take the sum of partial pressures. What is the partial pressures? We will understand this here with a certain example. Okay. So if you look at the atmosphere has this atmospheric air. In this atmospheric air, you will have certain component of nitrogen. Okay, about 70% is N2 in the atmospheric air, and the remaining 30% is mostly shared by the 20% with oxygen, and the remaining 10%, the remaining constituents like CO, the carbon monoxide, and the argon, and so on. Okay, so this is how your atmospheric air will be like. So if I want to calculate the pressure of atmospheric air, what I should do, I will take the pressure of individual elements here, that is pressure of N2 plus pressure of O2 plus pressure of CO plus pressure of argon plus pressure of so on the elements. So whatever the elements are there here, if I take the individual pressures, that individual pressures are nothing but called as a partial pressures here. So this partial pressures, if you take the sum, that will be giving you the total pressure of that particular mixture. Okay, this is applicable not just for the air, it is applicable for any other gas that is present there. For any mixture of gases, this is valid. That's what the Dalton's law of partial pressure says. So what it says is essentially, I can write it in the more common form. The more common form will be like P is equal to P1 plus P2 plus so on plus PC. Okay, let us keep calling it as PC for now, and this is how your expression will look like for Dalton's law of partial pressures. Okay, so how can we prove this? Okay, how can we prove this? So in order to prove this, let me assume homogeneous mixture of inert ideal gases all of them considered at temperature of T and the pressure of P and the volume of V. So these are the things that are considered here. For this I will apply the ideal gas equation here. So if I apply the ideal gas equation on my left hand side, I'll be getting P V, and on my right hand side I have so many gases here. That's why for those so many gases I have to take N1 plus N2 plus so on plus Nc. How many gases are there? So many moles you have to write. We are taking the sum of all those moles here, and since I have taken moles here, I should use R bar here, which is universal gas constant. If I use M here, I should use particular gas constant. Since I have N here, I am using R bar, and R bar T. This is the regular form of the equation that I have. So this equation PV is equal to N1 plus N2 plus so on plus Nc into R bar T. I will be writing it in a different form here in form of P. So P on my left hand side, and on the right hand side I will write the expression as N1 into R bar T by V plus N2 into R bar T by V plus so on plus I will get this expression as Nc into R bar T by V. So this is how I am going to get my expression, and this expression that I have here, sorry, yeah, this expression I have here N1 R N1 R bar T by V is nothing but my P1 plus P2 plus so on plus PC. So this is how I can prove the Dalton's law of partial pressures, okay, where P is the total pressure. There is some issue with this writing, don't worry. P is the total pressure, and P1 comma P2 comma P3 and so on PC are called as partial pressures, okay. So this is the basic understanding of our Dalton's law of partial pressures. Okay, moving on, we should also see the concept of total number of moles. Total number of moles. So when I am speaking about moles here, I am speaking about N here. Okay. So here I should take sigma N. So like I have shown here in this example here, so this N1 plus N2 plus so on plus Nc, this complete thing is called as sigma N, basically the sum of all the mole, sum of all N is equal to N1 plus N2, let me take the other color, N1 plus N2 plus so on plus Nc. So that's for how I will get my total number of moles. This question is asked. This is how you will calculate. That's a simple thing. And we'll move on to the next concept. The next concept is the concept of mole fraction. Mole fraction. This mole fraction is represented generally with x. Okay. So how do I write this? So this is again based on your sigma n actually. So this, if I take onto the right hand side and write 1 here, so what I will get here is n1 by sigma n plus n2 by sigma n plus so on plus nc by sigma n. So 1 is equal to this n by sigma n, n1 by sigma n I will call it as x1, and n2 by sigma n I will call it as x2. Similarly, I will call the remaining things and this will become my xc. So this x1 is nothing but the mole fraction of mix gas 1. X2 is the mole fraction of gas 2, and so on. We will have the mole fractions in this fashion. So to put it simple, the mole fraction is the ratio of number of moles of the given gas to the overall number of moles. Okay, so that's what the mole fraction is, and this sum of all the mole fractions is always equal to 1. Sum of all mole fractions is always equal to 1. Okay, so that's the thing regarding the mole fraction. So why this mole fraction and all, we'll understand it in terms of partial pressures if we express this in this way. Okay, like the expression that we have already taken here, the same expression we'll try to take here. This particular expression we have taken, right? So let us take this here. So in this expression we have this PV equal to sigma n into R bar T, right? This is what we have here, and this expression I will write in form of V is equal to, I will put sigma n here, R bar T, and I will take that P that's there on my this R bar and T are getting mixed, R bar T by P I will put here. The P that is there on my left hand side is taken into the denominator on my right hand side. Okay, so let us keep this aside and maybe let me call this as expression A. Okay, this we will use it later on, but before we use it, we should look at one of the partial pressures. We can take P1 or P2 or anything for that matter. So we will take P1. So the P1 is equal to N1 R bar T by V. Okay, this is the partial pressure like we have shown in the previous example. The same pressure I have taken here. Now what I will do, I will substitute my V in this place. Okay, in the denominator I will substitute this equation A. So substituting equation A here, so what I will get here is the P1 is going to be like N1 into R bar T by the V is nothing but sigma n and R bar T into P will come into the numerator now. So here now I can cancel out the R bar T here and R bar T here. So this expression of P1 will turn out to be, the P1 will be equal to N1 by sigma n into the P. So the P1 now can be written in terms of my mole fraction, the x1. So this is the purpose why we define the mole fraction basically. So we can calculate the partial pressure even using this mole fraction. Similarly, you will get the expression for the remaining partial pressures like P2 equal to x2p, P3 equal to x3p, and so on. You will have Pc is equal to xcp. So where left hand side I have my partial pressures is equal to the mole fraction, maybe fraction I will write it here, mole fraction into the total pressure. So that's how your mole fraction will be helpful to you in calculating the partial pressure. That's the use of your mole fraction. So moving on, so far we have seen this partial pressure concept only in terms of N, that is number of moles you have considered here. Okay. So now in place of N we will try to put M and see how this works out. Okay. So how the Dalton's law of partial pressure will be useful to you here in terms of M, that also we will try to see now. So for this purpose, what I am doing P1 V is equal to M1 R T. So PV is equal to N R bar T. PV is equal to M R T. So this we know for the universal gas constant and particular gas constant difference. Since I am using the particular gas constant here, I am using M here. So that's how I will write it for gas 1, and for gas 2, P2 into V into M2 RT. So here, since this is a particular gas constant, the gas constant will vary from gas to gas. It is not same like your universal gas constant. So I should take R1 and R2 also here, and so on. I can take it for PCV is equal to MC into RC into T. So likewise, you can keep writing it. So here, if I take the sum on my left hand side, if I take the sum on my left hand side, it is P1 plus P2 plus so on plus PC into V, which is equal to M1R1 plus M2R2 plus so on plus MCRC, and the T can be taken as common here, so I can keep it this way. So this is how I will get my expression. So if you look at carefully, this sum of the partial pressures is nothing but the total pressure, right? That's what Dalton's law of partial pressure says. So I can write the sum as P. The PV will be now equal to M1 R1 plus M2 R2 plus so on plus MC RC into T. So this is how your expression is like now. In order to reduce it further, now let us consider something called as a Rm here. Okay, if Rm is the particular gas constant of the mixture, if Rm is the particular gas constant of the mixture, then we may write this whole thing like this, because M1 R1 plus M2 R2 plus so on plus MC RC will now be equal to M1 plus M2 plus so on plus MC into Rm. So now the Rm can be expressed as M1R1 plus M2R2 plus so on plus MCRC by M1 plus M2 plus so on plus MC. So this is how you can express the Rm here. This Rm is the value of R for the mixture. Okay, this is one important formula which you may use based on the need here. So here, if you look at the denominator, this denominator can be named as total mass. This total mass will be equal to M1 plus M2 plus MC. So simply this is the thing here. And now if you would like to invoke this R M into this one here, this expression of PV now will become like this. So the PV PV will be equal to M1 plus M2 plus so on plus MC into Rm into T. So this is how your equation will be like when it comes to your M and R. Okay, so M means the mass and R means the particular gas constant or the characteristic gas constant. This is how you will write the expression of ideal gas equation. And moving on to the next topic within this fold is the topic of equivalent molecular weight. So in the same context, equivalent molecular weight is also an important thing which will help you understand the overall picture here. So for this purpose, you will be taking the product of N into the molecular weight. N into molecular weight will be equal to, so before I write this, maybe I can probably write it like M is equal to, then it will be more clear. Like I have written this expression here, M is equal to total mass. The same expression I am writing here, M is equal to M1 plus M2 plus so on plus MC. So this M is nothing but my N into molecular weight, right? So here I'll get N1 molecular weight of 1 plus N2 into molecular weight of 2 plus so on plus Nc into molecular weight of C. So this is how I will get this expression. And in this expression, if I take my N onto the other side, so what I'll get here is MW, that is molecular weight, that is equivalent molecular weight I should say, strictly speaking, is equal to N1 by N. This N1 by N is nothing but your X1 as we have seen in the mole fraction previously. So X1 is nothing but your mole fraction. So X1 into MW1 plus X2 into MW2 plus so on plus XC into MWC. So this is how your expression will be like for equivalent molecular weight. This is the expression for equivalent molecular weight, and this molecular weight formula, this molecular weight formula can also be written in a different form, like simpler form, where you will have molecular weight is equal to sigma x into x of, let's say, any particular k, okay, into molecular weight of any particular k. That is, you will write it for 1 plus 2 plus 3 plus 4 and 5 and so on. This is another way of representing the same thing in a simpler form. So this is the story of your equivalent molecular weight. And in the same context, it is also important to understand the concept of partial volume. Partial pressure we have seen so far. So partial volume is also an important concept here. If you want to understand this partial volume concept, it goes like this. You can have a bigger volume, something like this. In this bigger volume, there can be so many other smaller volumes like this one and this one and this one and this one. So these are all the simple chambers, I should say. These chambers can have holes. Sometimes when the holes are made for these chambers, all the gases will get mixed. Okay, so now let us say they are not mixed and they are having their own volumes, and they are having same pressure P and same temperature T. If that is the case, how should I write my PV is equal to MRT here. In that case, I will write the PV is equal to MRT for 1 as P1. So PV1 is equal to M1 R1T. So P and T are constant in this case, are same in this case. That's why this P and T are taken as the common and the constant things. If I write it for 2, PV2 is equal to M2 R2T. So this is how I will write. And then moving on, I will have P V C equal to MC RC T. So this is how I will get the expressions for each individual gas. Now I will take the sum on the left hand side. Sum on the left hand side, I can take it with P as a common into V1 plus V2 plus so on plus Vc equal to M1 R1 plus so on. Maybe I'll write M2 R2 also here. M2 R2 plus so on plus MC RC into T. Okay, so this is the expression that I am getting here in terms of partial volumes. Okay, so in this V1 V2 V1 comma V2 so on Vc are partial volumes. Sometimes the problem can be written in this manner also, and here we can get something called as total volume. The total volume V will be equal to the sum of all the things. Simple again, nothing great. My pen, go down. Yeah, thank you. So V is equal to total volume, which is equal to V1 plus V2 plus so on plus Vc. So this is the story of your partial volumes, and that the same is expressed as a total volume. And one more concept in relation to this is specific volume. I think I erase this. Of mixture. This may also be helpful while solving some problems. So the V is expressed as V by M. The specific volume small v is expressed as volume per unit mass, that is meter cube per kg. Okay, that's how you express it regularly. The same V by M that we are taking here, so the V is equal to capital V by M is equal to V by M1 plus M2 plus so on plus MC. This is how I can express it. And now the same thing I will write it like 1 by V here. Why I am writing you will understand in the next steps. So bear with me, take me for granted for now. And MC by V I will get here. So in this expression, now what I will do is 1 by V is equal to M1 by V plus M2 by V plus so on plus MC by V. I will get, I should write V only, not VC. So here 1 by V will now be called as 1 by V1 here plus 1 by V2 here plus so on plus 1 by Vc. So this is how I'll get my expression for the what I should say, mixture of specific heat, mixture of gases for specific heats. So this is the expression that you are going to get here. Okay, so based on the same thing we will get one more concept here called as density of mixtures. Density of mixture of gases. So that is, we are speaking about rho here. So for this purpose, we already know that 1 by V is nothing but rho. That is, rho is nothing but kg per meter cube. Rho is nothing but kg per meter cube, and V is nothing but meter cube per kg. So it makes sense even in terms of the units. So 1 by V is equal to rho. So because 1 by V is nothing but mass by volume. So density is nothing but the mass by volume. So it makes sense there. So what I can do is, based on the expression that I obtained here, I can write that the rho, overall rho, will be equal to rho 1 plus rho 2 plus so on plus rho c. So in order to summarize what we have seen so far, if I have to take the pressure will be taken as the sum P1 plus P2 plus so on plus PC. Okay, and if you have to take the volume is also taken like V1 plus V2 plus so on plus Vc. And if I have to take the R Rm of the mixture will not be like this. It has to be taken like M1 R1 plus M2 R2 plus so on plus MC RC by M1 plus M2 plus so on plus MC. So that's how you should take the R. Okay, for pressure and volume, simple sum. But Rm, this is how it is taken. Even when you take N is taken as N1 plus N2 plus so on plus NC. And if you take M is also taken like M1 plus M2 plus so on plus MC. And temperature we cannot speak in these terms. So in your PV is equal to MRT and PV is equal to N R bar T. So in this particular expression, we spoke about pressure, we spoke about the volume, we spoke about the R and R bar, and we also spoke about the M and N. The temperature is anyways the same. It is going to be the same for all the gases, for the gas mixtures. It is same if it is mixed for a long period and it is maintaining to be the zeroth law of thermodynamics. Temperature is going to be the same for all the gases, and there can be circumstances when they are not mixed. When they are not mixed, they will have individual temperatures. They will be given in the problem. And here, this is how you will take it for R. And since you have taken it for R, the same R concept for R bar also you can take here, because R is nothing but R bar by molecular weight. R, the same expression can be written as R bar is equal to R into molecular weight. So this Rm expression that I have written here can be modified accordingly based on your need, based on your molecular weight here. Based on the molecular weight, you can transform the expression accordingly. So in the PV is equal to MRT and PV is equal to NRT, we spoke about everything, how they vary for a mixture. Okay, so with this idea, we can solve any given problem. So these are the concepts. To solve this problem, to understand this concept, well, we will solve a problem here. So we'll take up this problem initially, and then we'll solve the other problems if the time permits. So here goes your question. So in this question, he has given that the vessel has a volume of this much. Okay, the overall volume he is giving. He is not giving the volume of the each individual thing. So I can write V here. I need not write V1 and V2 here. I can directly write V, which is 0.35 meter cube, and then contains 0.4 kg of carbon monoxide, he is saying. So this M he is giving only for carbon monoxide. So this carbon monoxide, I will be calling it as 1 throughout this question. So I will call it as M1, which is equal to 0.4 kg. And the molecular weight of this carbon monoxide is also given, which is 28. So the molecular weight of the carbon monoxide is 28 kg per kg mole is the unit. Okay, and 1 kg of air is given. M of air is given, which is 1 kg, and the temperature is given for the overall mixture, which is 20 degrees centigrade, and you should always convert it into Kelvin. So plus 273, if you do 293 Kelvin you will get. So 20 degrees centigrade is clear, and he's asking you to calculate the partial pressure of each constituent and the total pressure in the vessel. So what he's asking you to find means, what is the pressure of one, pressure of the other things. Actually there is oxygen and nitrogen also, so you will have P2 and P3 also here. So I will call the oxygen as 2 in this question and the nitrogen as 3 in this question. So P1, P2, P3 he is asking, and he is also asking the overall pressure in the second question. Pressure overall or pressure total is asking you to find. So that's the question is given to you, and here this 23.3% of the oxygen he is saying. So whatever the air that is there here, this air has 23.3% of oxygen plus 76, what is it, 76.7% of nitrogen. So I can imagine my problem like this. If this is my complete capacity and it has 3 chambers, and in the first chamber I have CO, that is carbon monoxide, and the next chamber I have O2, and in the next chamber I have N2. Actually these two are not given separately, they are given as a mixture directly. Of course the CO is also mixing with it. At the end of the day all the three are mixing with each other, but for the sake of clarity I am showing it to you like this. And for CO the mass value given here is 0.4 kg, and the oxygen value I should get here. So in order to get that oxygen value, that is M2, will be 23.3%. This percentage is nothing but my by 100, right? So I can write this as by 100 into 1. So that will be giving me M2 equal to 0.233 kg. And similarly if I do for M3, I will get for 76.7% 0.767 kg I will get. So here what I have for M2 is, the M2 is 0.233 kg I have, and N2 is 0.767 kg I have. So this is the thing that is available to me here, and based on this I will have to calculate the partial pressure of the each constituent here. So for calculating the partial pressure of each constituent, I will take the formula of P1 equal to M1 R1T by the volume. Okay, if you look at this particular formula, M1 is known and the R1 should be known here. In order to calculate the R1, I can use R bar here. Okay, so what is the relationship between R and R bar? R is equal to R bar by the molecular weight, the corresponding molecular weight. So the R bar value is 8.314 kilojoule per kg mole Kelvin, which must be remembered, which must be by hearted. And then the molecular weight of the CO is given in the question. I think it's 28. Yeah, it's 28. It's given in question. So let us make use of the same 28 here. So that's how you will get R1. The temperature is 293 Kelvin given in question. The volume is also given in question as 0.35. So you can substitute all the values here. So the P1 will be equal to 0.4 into the R1 is 8.314 by the molecular weight is 28 into the temperature is 294. Let me see that 293 by the volume is given in question as 0.35. So that will give me the pressure of carbon monoxide, which will be equal to 99.42 kilopascal. Okay, I made this calculation in my calculator, so you can do it in your calculator and you will get it. So similarly you can do it for P2. So the P2 will be equal to the P2 will be equal to M2 R2T by V, which is equal to, again the M2 value is 0.233 and the R2 value is 8.314 by the molecular weight of oxygen should be taken here. For oxygen the value is 32. The molecular weight of the oxygen should be by-hearted, that is 32 kg per kg mole. You should remember this value. And the temperature is given as 293 in the question and the volume is given as 0.35 in the question. So you will get this as 50.68 kilopascal. You do the calculation for yourself, you'll get that. And then comes the P3. I think this somehow I will write it properly here. For P3 is equal to M3 R3T by V, which is 0.767 into 8.314. The molecular weight of the nitrogen, should be by hearted, which is 28. So you should remember the values for oxygen, nitrogen and CO2. So they are not given in question. Oxygen 32 is the molecular weight and the nitrogen the molecular weight is 28 and the CO2 is 44. This must be by hearted. They will not be given in the question. You have to remember and substitute. The volume value is 0.35 meter cube given in the question. So you can substitute that directly and you'll be getting 190.65 kilopascal. So that's how you'll get the P1, P2, P3 pressures. So that is a data being asked to you. So maybe you can highlight that. This is the thing that is being asked to you. And this is P2. Let me correct it like this. P2. There is some glitch it seems. Anyways, that is P2. And then this is P3. So yeah, these are the three things that he's asking you to find. You have found them out here. P1, P2, P3 are given to you here. This dabba is not nice. I can leave it, but yeah, okay, this is much better. Yeah, so that's the P3. So P1, P2, P3 values asked in the question are found out, and he's also asking you to find out the P total. So if you have to find out the P total here, the P total will be P1 plus P2 plus P3. Take the sum of all these things. So when you take the sum of 99, 50 and 190, you will get that value to be, so the P total will be 340.75 kilopascals. Okay, so this is the thing that he's asking you to find. So you have found out all the things that are asked in the question. So it is quite simple. So that's how we will solve these problems. Okay, and we'll see one more problem. So the one more problem, I'll copy it from this here. Let's see how it's get copied. And let me go to my OneNote, and here I am pasting. Yeah, it's fairly good. Let us increase the font size. Yeah, I think the font size is clear enough now. So this is one more question. Maybe we can write this as question number 2. And he has given a 1 kg of air here. M is equal to 1 kg. That's the given data. And he is also given the percentages here. These are the percentages of various things, that is the oxygen, nitrogen, argon, carbon dioxide. And he is asking you to calculate what is the gas constant of air for these molecular weights. So gas constant of air formula we already know, the R of mixture. Air means air is a mixture here. So this one will have this sort of formula here, M1 R1 plus M2 R2 plus M3 R3 plus M4 R4 by M1 plus M2 plus M3 plus M4. This is how you should take that formula, because there are 4 things. I have written this for 4 things. Okay. So there are 4 constituents. So you will write it for 4 constituents. For this you have to find out what is the M1 value here. The M1 value will be based on its percentage. The percentage for this M1 is 23.14% into the 1 kg. If I do that, I'll get 0.2314 kg, and similarly I'll get M2 as 0.7553 kg, and M3 as 0.0128 kg, and M4 as 0.0005 kg. Okay, so these are the M values that you are getting here. Also you need R1 R2 values here. The R1 is equal to R bar by the molecular weight of that particular thing. So R bar is 8.314, and the molecular weight of the first body is given as 32 in the question. Actually this is oxygen, which you should remember. Actually need not be given in question. So the R2 is similarly 8.314 by 28 for nitrogen, and the R3 is 8.314 by 40, and R4 is 8.314 by, I guess it will be 44. Yeah, the 44 for carbon dioxide. So the R1 values are known, M1, M2, M3, M4, all the values are known to you. Just you have to substitute all the values into this RM, and then you'll get what is the value of RM. The RM value I have calculated here. Where it is? Yeah, here it is. The RM value I got it as 0.2871 kilojoule per kg Kelvin, Actually, this value is a very well-known value to you. It is nothing but the Cp minus Cv value 0.287. Since this is given in a problem, you have done all this calculation, but this number is generally by hearted by any student, so you are supposed to remember this number. Okay, and the same concept you can apply for any other mixture for calculating the gas constant of the mixture. And he's also asking you to find out what is the apparent molecular weight. Apparent molecular weight means the molecular weight of the mixture. Molecular weight of the mixture, if you have to find, that will be like R bar by R, right? That is Rm that you have found out. So the R bar value is very well known. It is a universal gas constant 8.314 by the Rm value 0.2871. So you'll get the molecular weight of that particular mixture. Here the mixture is air. So for molecular weight of air, you'll get around 29 or 28. The value is here. The exact value is 28.96 kg per kg mole is the molecular weight that you will get here. For air, you should remember this value also, and this value will be very close to the value of nitrogen, because nitrogen is a major constituent of the atmospheric air. Here in this problem also, he has given the similar thing to you here. So the nitrogen has about 75%. So since it is close to this percent, so your molecular weight of this thing will also be close to this one. So the major component will have the major influence here. So the molecular weight is very close to your 28, and it makes sense. So your answer is right. So this is how we will see the questions based on the Dalton's law of partial pressure. There can be other questions as well. I request you to practice the remaining practice problems accordingly. Thank you. We'll meet you in the next lecture. So before I move on to the next lecture, let me show you the syllabus here. The syllabus goes like this. So we have completed the Dalton's law of partial pressure. In the next class, we'll see the internal energy concept. Thank you.